Yes, sir.
So I,
Yeah, we can start.
yeah. So I
Organizing
share.
things.
So
Yeah,
I
just
share
wait, sir. Wait,
presentation.
wait for a minute. Yeah. Organizing things,
Okay,
please.
sir. Yes, sir. A very good morning to one and all. I welcome you to this eighth session of this online faculty development program on 3D printing and design, sponsored by All India Council for Technical Education's Training and Learning Academy under Azadi Ka Amrit Mahotsav and IQAC SPC. It's my privilege to introduce you to our today's eminent speaker for this section, Dr. D.K. Shinde sir. Dr. D.K. Shinde sir is an associate professor and head of production engineering at Veer Mata Jijabai Technological Institute, VJTI. He is also an associate of professor in industrial production engineering, having 19 years of experience. His research field include process modeling in composites, nano-engineered materials, and nanotechnology, electrospinning, molecular dynamic simulations for polymeric composite materials, multifunctioning materials, low-cost composite manufacturing, mechanical characterization of materials, computer-aided design, finite element modeling fatigue, impact modeling and testing of polymeric composites, micromechanic, etc. He has received the Best Startup Award by World Trade Center Mumbai and Chamber of Commerce and Industry on March 2nd, 2019 in the International Conference on Business and Startup at D.Y. Patil University, Mumbai. He's also received the Best Dronacharya Award for Mentoring Innovation Product for Smart Navigation Band at National Level Entrepreneur Competition organized by Jaro Education Mumbai on 29th of January 2019. He has received Dr. Vadaran L. Kennedy Scholar Award, North Carolina A and T State University in the year 2012-13. Further, I now request Dr. D.K. Shinde sir to kindly commence the session. We warmly welcome you, sir.
Uh, is it audible?
Yes, sir. You are audible.
Yeah.
Our
So good
presentation in
morning.
PPT mode, sir. So
Okay,
it is
sure.
not in PPT mode yet.
Yeah, 1 second.
Yeah, it is in PPT mode now. Yeah, you can
Yeah.
go ahead.
All right. So very good morning to all of you. First of all, I thanks to the coordinator of this, Atal Faculty Development Program organized by Dr. Kiran Bole sir from Sardar Patel College of Engineering, Mumbai. So this is the second inning. What we are doing on the 3D printing FDP at SPC. We had earlier in the September 2021. So I welcome all the participants for this morning talk. So thank you for this introduction. And now let's go with the today's talk. I have planned for the next 2 hours. So it will be like a, huge bombarding on you, but you must learn something from this session. So today I will be talking more about this 3D printing on the polymeric parts, which involve the nanocomposite, and we will take what is the prospect and what are the challenges to be in 2030. That I will talk little bit, and I will cover, instead of going the all such kind, the theoretical background of fuse deposition modeling methods, how does it work, but I will utilize those method and whatever the nanocomposite we have prepared or fabricated using the 3D printing method. Few of those are like ABS with CNT, ABS with graphene, and then I will go through some more development on continuous fiber 3D printing processes for aerospace application point of view from the Lockheed Martin and other group of United States. Large additive manufacturing from the United States, few of those additive manufacturing organization working continuously to build the mega structures and develop such kind of component with cost effective and properties. established in 1887. This is very old institute in Mumbai, which also gave birth to the many IITs. IIT Bombay also established by the VJTI, faculties, and director of IIT in the founding year was from the VJTI. So this is a very old institute. Earlier it was called as Victoria Jubilee Technological Institute. 1999 it has been converted to the name of mother of Chhatrapati Shivaji Maharaj, Veer Mata Jijabai, and now the acronym remains same, VJTI. So we are here, and I did my PhD from North Carolina State University, USA. So this is what the US map, and this is the eastern side. North Carolina is here, and we are located in Greensboro campus of North Carolina. So the school in which I did the first PhD in nano engineering was Joint School of Nanoscience and Nano Engineering at Greensboro campus is set up, which shown over here. So this is VJTI is having few UG PG program. We stood among the NRF ranking of 82 number and REI ranking of 5th in the Government Engineering College in the year of 2020 ranking, and 82 in the rank of NRF 2021, and many more activities going on from my institute side. I belong to the Department of Production, established in 59, and a few of those programs which we run at our department is BTech, MTech, and PhD program in the Department of Production Engineering, VJTI. All right, that is from my side. Little bit I always give the small introduction of my department, my institute, what we are doing, and from where we are coming from. So now it is time to start with what is the nanotechnology first, to understand. Most of you may be knowing, but I will again take you through the way which I understand. I want to present the nanotechnology. So Richard Feynman, the first person in 1959, he gave the idea who talk about more about like why can't we write an entire 24 volumes of encyclopedia of Britannica on the head of the pin, and he said there are a lot of or you can say the plenties of room at the bottom where you can do things and you can bring and develop the things. And from that onwards, people start working with developing stuff at the nanoscale. What we say is is the creation of functional material devices system through the understanding and control of matter at a dimension in the range of nanometer, like 1 to 100 nanometer, where new functionalities are developed, new properties are coming to the because of the matter, and observed. Those matters property can be harnessed for the broad range of applications, and therefore we say it is art and science of building a stuff that does the stuff at nanometer scale. That's what Richard Samley gave the definition, and few of those examples what we see here in my molecular dynamics simulation in the material studio. This is engineered DNA strand by joining the atoms to prepare a DNA strand with the help of this particular molecular modeling at the nanoscale. Then you see the RNA tiny motor, which has been created with the help of DNA is inside, RNA is outside, and then you can see those right hand lobes and the left hand lobes, and then how you can prepare pRNA tiny motors with the help of nano stuff at the nanoscale level. This one is also semiconducting metal junction formed by 2 carbon nanotubes which are connected, so you can join it by using, this is also modeling done at the initial level to see that one. So what is the nano? Nano is nothing but it's a 10 to the power 9 or 1 billionth of meter, you can say, and that much small size. We know micro and those micro sizes and micrometers we have seen under the microscope to see those, but to do this work we need some kind of scale what is been specified for this particular technologies. We take 1 to 100 nanometer, but we cannot see everything under the naked eyes, so we need equipment, microscopic equipment called as scanning electron microscope, then tunneling electron microscope or atomic force microscopy, AFM, TEM, SEM, are required to see and manipulate those things at the atomic level, and therefore to do more work at this bottom of the level. So if you say in the size, if you take the example of 10 to the power minus 9, a person is normally walking 32 kilometers, like 6 foot 5 inch a person is walking. So it may walk 32 kilometers in a day of 24 hours. If you shrunk the same person 6 feet 5 6 inch to a 1 nanometer, how long that person can walk? And if you take that walk on dollar of the bill, and how long it will take to reach. So that's how the small thing you can think about that, and the person will take almost like 24 years to walk on that 10 rupees of note, or you can say $1 of note, on which a person who is shrunk to a nanometer size, 1 nanometer, so it will take 24 years. And that's how the smaller the things, how it plays an important role. And you can think about what's the small thing it will take a time to reach on this particular 10 rupees of note, or which is equivalent length in the $1 of bill. So this is how little bit about nano. So in nanotechnology science and the science, we can say this is science of manipulating atoms and molecules, which are shown in some of those early examples. So that is creating many new material functionalities and devices. And then this particular approach will be helping us interdisciplinary approach to develop various nanomaterial which can be used to enhance the existing material properties, as well as build the new systems and devices. Few of those are nano ribbons. This is a buckyball, and these are the nanotubes has been shown over here. If you compare it quickly from the right hand side to the tennis ball to the smallest size in 0.1 nanometer, which is a 1 angstrom. So if you go with the period, what we always put using our writing pen is 10 to the power 6 nanometer. Then you go to the cancer cell, 10 to the power 10 nanometer, 4 nanometer. And then if you go the bacteria, 1000 nanometers, and then viruses, what is the pandemic we see right now is like 400 to 500 nanometer size. Those viruses are coming, and we are going beyond that one to make 100 to 1 to 100 nanometers. So in this funnel, if you see what are the materials which are stable at this particular scale with the energy and other properties and derives, and these properties, these derived properties can be harnessed to make the new material, such as those materials which are contributing for the giving the new properties are nano devices in the group what we may be using right now, and few of those are already started utilizing are your nanopores, dendrimers, nanotubes, quantum dot, and nanocells, which are shown over here. So now the things which you compare on the man-made as well as your natural things. So your dust mite will be 200 micrometer, art is 5 millimeters. Your hair of human is 60 to 120 micrometer length, diameter. And then you have the blood cell is 2 to 5 micron, and then you have the diameter of this particular peptide cell what you have created is 10 nanometer diameter is shown over here. RNA 2 to 12 nanometer diameter DNA has been created, and same thing you can synthesize by using the atom manipulations, molecule manipulation with the help of your manipulator in the AFM, biologically SEM, or regular scanning electron microscope, or you can use the other available microscopic tool to manipulate it. And if you compare from this nano world to the micro world, and you are reaching over here, so those are the things which we are right now, due to the availability of the equipment, we are making like quantum coral of 48 iron atoms on a copper surface has been placed with a nice quantum coral which was seen like this, and then color image is shown over here, was been created by the IBM using the STMs, so scanning tunneling microscopy tip, to make those coral diameter of 14 nanometer size. Then few of those which are things are made by using the available synthesis method is carbon nanotube, bucky balls, Then you have the graphenes. They are being used as a connector in the today's computer processors. Then self-assembly molecules, which are been widely been used for developing the drugs and biological material, as well as create some of those, SAMs, what we say, self-assembly molecule kind of, synthesis using the bottom-up approach. So those tiny motors, MEMS devices, what is been manufactured using the lithography methods, and those lithography can be, making small tiny devices, and you can utilize it. So this is little bit about, showing the comparison of the your scale, what we are having to understand about the. This is how you can see the clear image of the human hair versus the nanofibers which have been produced by the using the electrospinning methods. So this is the diameter you can see compared with this. So these are the very tiny. So the properties which are developing in the nanomaterials are because of the smaller in the size, larger is the surface area, more is surface energy and interaction with the other elements in the complete system, and therefore this availability of the smaller in smaller in size, which are quantum dot, quantum veil, and you have the tunneling the through the channels. So many applications which are developed through the 1D, 2D, and 3D materials. So smaller size has many good properties which are stabilized properties and can be utilized to develop the new material with the help of those. So let's go with Nano 1, Nano 2, and Nano 3, which came from 2000 to 2010. Nano 1, then 20, Nano 2, and we are in the era of 2030. So these are the few of those national initiatives, the functional, national initiatives, which gives the idea about last 20 years and entering in the 30 years of, bringing those quasi-exponential growth of nanotechnology in the, various discipline, vertical science to the technology transition and horizontal expansion area in the various fields such as textile, cement, agriculture, and spinning off many of those, areas, namely like nanophotonics, metamaterials, which is, batteries and battery developments are going over here a lot from this particular analysis. Or the synthesis of this spinitronics and nano sustains are also coming, and science nanotechnology promises now to build the new areas and material in the design and manufacturing which are coming over here. So this also shows first phase which came in 2000, which is a creative phase. Then you have the integration phase, and then we are now in the form of innovation phase, which is generating the new material systems, and which can be coming in the 2030s area, which will be having the lot of contribution in terms of revenue. Is the new product application like $30 trillion, which will be coming in this area 2020 to 2030. So basically here what we did, the bottom-up approach and top-down approach to develop the material, and a lot of synthesis and structuring the material has been done as knowledge of influence, and then assembled those material to build the new materials, and it has given the idea to develop new kind of your systems and devices, which will be coming as a nanotechnology generation, 6th generation of nanotechnology. So this is how the innovation phase is helping us to bring the new materials. So vision inspired research is now changing from the conventional way to the vision inspired research by adding those nanotechnology initiative has been shown over here. Few of those the representation in last 30-year development, if you look over here, it's changing the focus and priority to converging the knowledge and technology for societal development is coming over here. Few breakthroughs underpin of the grand challenges which came with the few of those, like making those millions times smaller than cancer treatment, which was a very tedious process to go through those therapies and all those. Now you have the drugs, you can deliver at that drug and you can cure it. Material 10 times higher strength than the existing material has been developed. Phenomena, the devices are coming with the nanophotonics, nano components, quantum fluctuation between the selected material and material surfaces are almost those frictionless material are coming in the magnetic computing. Also million times less energy consumption is required. How the developed country like United States, few of those president spend more budget on those nanotechnology, from the Clintons, Bush, Obama, Trump, and now the 30s 2030s era. Biden is also giving the higher budget to the nanotechnology innovation and initiative to bring the technology development and make the energy sustainable goal of United Nations. So this is again concisely put over here. Passive nanostructures, active nanostructures came in the first nano 1, nano 2 system of nanosystems, molecular nanosystems, and then technology which are coming through the integration of all the available material and structured material. So nanotechnology convergence is going on to produce the generation of new nano products which will be coming in the coming this 2030s decade. So what is required was, in this case, infrastructure, workforce came, and then discipline and new industries and societal impact happened. Now here new products and services are coming, and few of those, if you see the just flash on those nano ones, what the quantum those quantum effect repulsion forces of which came from the Harvard University synthesis mechanism, how to synthesize using bottom approach and top down approach using chemical vapor deposition, came from the 2009 PANSAS. Then few of those what the Moore's law came in 2000 to tell about how this development is going to occur in the coming days, or the development of processor in 2000, and now you see the processor development which are coming. So those 1D, 2D, 3D and 4D devices, material development which are occurring and has been noted, so I'm not going to repeat it. Nano 2, those synthesis and again integration based on nanosystems came in the form of this kind of 12 atoms. You can see the nanofluidics has been developed to channel the nanofluids and get those flow of those or taking the sink out of the heat generated in the today's processors. Then nanosystems in health and environmental devices are coming. So these 20 and 30s, many systems and devices which has been came in the form of biomimetics based or biorobotics or neuromorphic or adiabatic switching for the ITs and quantum systems. So these are like people are working continuously in the new systems now right now, and we are also going to develop our 3D printing material with the help of available this material, and that's how I'm emphasizing to understand what the world is moving and where we are and how the people are moving forward. So regenerative medicine, gene editing, 3D printing parts, what we want to develop the genomics, material genomics or gene 3D printing of the genes can be done with the help of biomedical material. 3D printing is the one of the area growing, and people are working to develop the cells and implant such kind of cells by biomedically printed material in the bodies to cure the immediate such kind of diseases, basically the cancer and all those are coming in this one. So these are a few of the publications and growing fields. I'm not going to talk more on that one. A few of those countries which are contributing for the research. So then penetration of nanotechnologies, how it happen in terms of the percentage of patents. So basically many patents are coming, so you have a lot of scope to develop the new material and file the patents. That's what I want to encourage from this slide, few slides which are coming. So US, China, Europe and Korea, they are majorly filing the patents and getting more journal and patents, and that's how the material develops, and they are leading to the technology world for use of nanotechnology to make the new systems and devices right now. So these slides you show, you can see from the patent applications how it is growing and what's the product market has been captured. exponentially the market is still, this growth is exponential is occurring. So look over to this one. In 2000 it was $40 billion of only the market was there. Now at 2020 it is $3 trillion, and still it is growing, and it can be bigger than that. So from the passive nanostructure, active nanostructure, and overlapping of those and nano systems by design is coming, and people are investing a lot. So there are a lot of scope for new guys who want to build their career and have the nanotechnology background. So material and manufacturing people are working a lot, and therefore if you look over to those per capita, so income, so in terms of this, few of those patents filed by the various years is shown over here. So in US and China, if you can see those kind of filing rates, and South Korea, so these are the majorly now working on that one. This is little bit about what I have planned for to understand more about is the nanotechnology and how it is going on. So let's go with the first I want to present to you the mechanical and electrical properties of carbon nanotube based acrylonitrile butyl styrene ABS material, what we say nanocomposite, which are fabricated using fused deposition methods. This paper is already published in a Scopus publication of SAMPI in 2019. So what we did, we have little things to share with you is the fused deposition modeling process. You have understood from the few of those presentations and talk from the couple of days on So the most recognized form of 3D printing of the thermoplastic is commonly known as the extrusion method, where we develop a lot of component, and same can be done with the help of my fused deposition modeling method by the extruders having a nozzle self-heated for the filament to melt out, and then deposit layer by layer and cure it, that is solidified, and deposit the another layer. So it will take the control over the feed as well as the temperature, and that's how we can make the layer by layer. This is a substrate on which build tray. You have support material you can have, or you can directly deposit on this one. So these are the spool which are unwound and pass through the nozzles, and you have the 3D printer head in which the heating arrangement is made, and there is a 1.75 millimeter of hole of that nozzle through which the melted solution will be coming down, and you can keep depositing using your XYG movement of your extruder is the best way to deposit. And few of those example, if you see from this, is captured from the various internet site and brought at one place to understand how the things can be built using those kind of different material. So few of those prototypes. So you first of all develop the 3D model, then you do the slicing using the STL file and upload the STL file, and then queue your material and check your all parameters, and entire 3D printing can be completed by layer by layer deposition using this particular fused deposition modeling. So you have a lot of scope in the construction area, automobile, people are working, aerospace. Nowadays people are reducing the many component to make the lesser component in the assembly, so as to increase the reliability and efficiency of the highly reliable and critical component in the aircraft. For example, if you take the example of your aircraft engines, generally the GE may manufacture most of those Boeing aircrafts engine, and they have converted mostly like 1,000 component to the like 300 200 component kind of assembly of the engine, and they join the sub assembly, and that's how less the number of parts, lower the chances to fail those component, and higher is the efficiency. And that's how the 3D printing will be helping you to develop such kind of components. So this is what we see, few of those, heart has been printed using those kind of polymer material. has been shown over. There are many over there. So this is how it look like. So if you see over here, so first you generate the CAD model. So this is a frame and X, Y, and Z coordinate system, Z code and M code you gives, and you generate the code, and that is how we feed the code to this particular processor, and processor control those the movement of your extruded in X, Y, and Z direction. And you have the substrate. So first foremost is CAD model to slice it, and then you can have your slicing of that STL file, and that STL file if you feed to your computer, and then it will be depositing one by one layer, and finally we'll be getting such kind of typical model what we have created in the CAD model. So how does it exactly deposited? You can see in this 3D pictorial view. So this is a bottom platform. So this can be moving up and down, layer by layer depositions are shown with the clear clarity of the layer 1, 2, 3, 4 like that. This is a shape, and this is how it will be coming from your and then once it is deposited, either to quickly cure, we need to use the laser or maybe some other UV light to cure it, and you can deposit the another layer, and that's how you can save the time and material wastage very easily from this kind of. So the liquid photopolymers is the shown over here. Then you have those X-ray mirrors, and laser beam will be helping to cure quickly and build such kind of components. So the internal structure, if you look over here, fused deposition modeling, what we use over here is those rollers will be taking care of feeders. So feed rate will be controlled. The challenges are in the self cleaning is the main challenges in the clogging of those nozzles has been now people are addressing a lot to develop those self cleaning at a certain interval of time, self clean it and again start redepositing is coming over. So this is how the parts will be built, but still the roller we need to take care of continuous maintenance of this one. And heating zone, these are the coils of the extrusion, and nozzle cleaning. So they have some mechanism attached with this one. So they self clean, again they feed it and then start depositing after certain interval of time. And that's how the time has been saved a lot in the 3D printing. So few of those laminate, manufacturing. So how to laminate 3D printing laminates. So prepregs you have. So you deposit those prepreg on those particular mask what has been prepared to develop that one. So it completely the prepreg will be coming. So this is what the you want to print the part like this one having a hole and this kind of geometric shape. So you pass this ray one layer and then expose with the laser, and this much part will be hardened, rest will be may not be cured, and then you can take out this particular layer. You pass another, then you can deposit. So like that, you can have laminated object manufacturing also by using the 3D printing method. So from here the material is coming, and the waste out roll will be here on this particular side, and your part will be built. And this is how we initially give the heat, but curing will be majorly done by the this one. So in this our 3D printing manufacturing, what we use the divide by zero AccuSoft system, 3D printing system we use to. This is a dual extruder 3D printers which we have in our laboratory to manufacture the ABS and mixed with the carbon nanotube. That's what I'm going to demonstrate it. So certain weight percentage of adding of those multiple carbon nanotube has given from the literature, improving the properties of the material. But how do we customize such kind of spool is the major part of this research. So what we did, we customized particularly with adding the certain varying weight percentage of the multiple carbon nanotube to characterize the material, to see what mechanical and electrical properties are been improved. So that was the major goal. So Why did we choose the ABS? Is ABS is widely been used in the automobile body part, dashboards, wheel covers, and many other cheap material which required and easily you can develop such kind of material. So styrene, this styrene acrylonitrile, it presents the polybutadiene, and that gives the shiny surface, and also has a rubbery substance and provides the resilience to the lower temperatures, and therefore this material has been widely used. But our goal is to improve the mechanical and electrical properties of existing natural ABS material, and that's how the goal was to develop both the characterization of the synthesis and characterization of CNT and graphene based acrylonitrile, butadiene, styrene, nanocomposite using this one. So this is what the people are using: carbon blacks or graphene oxide and other oxides they are using for many applications to develop the new material. But in our research, what we decided to use the 3D printing of those material using the carbon nanotubes. So we took the three major weight percentage of multi-wall carbon nanotubes. We bought it from the suppliers from the Faridabad as well as the Jharkhand, and we did the characterization despite of the characterization sheet given by the manufacturer synthesizing agencies from the source. And then we selected three weight percentage: 0.1, 0.2, and 0.3 to add in the natural ABS and prepare our spool. Customized spool was the first stage. So how did we do that? One is we have the pallets of the particularly ABS, and then we added three weight percentage: 0.1, 0.2, what we have shown over here, 0.1 weight percentage, 0.2, 0.3 weight percentage of the total weight of the spool. Let's say spool may be having like 2 kg, so we added like that weight percentage, 0.2, 0.3, and we prepared. So this was the rota mixer in which we poured the CNT in the pallets of the ABS, and that was mixed properly so as to disperse. And this particular image shows that the carbon CNTs has been stick with those pallets. Now these pallets will go through the extrusion process to prepare our wires, spool wires. So this is hooper where that mixture has been poured, and that is heated to the extruder, and then it goes through the 3 pages: first water tank, second water tank, and then diameter measuring, and finally this windings was collected on the winders. And this is actual machine images having extruder with the different zones shown over here, which will be passing, and molten metal will be pierced through this particular die hole, and wire will be continuously pull out. And due to this tractor, we would wind it on the winder with the speeding, and we can have the particular spool from that one. Then once that spool is made with the 0.1, 0.2, and 0.3 weight percentage, then it will be taken to print the 3D printing parts. So directly what we did we want to do the material characterization, so we use the ISO ASTM. We followed ASTM 368 standards to print the specimen size directly rather than preparing a sheet and then cut it. So we directly printed 3D printed the dogbone shape of coupons of both natural ABS, 0.1 weight percent, 0.2, 0.3 weight percentage of those spool. So then these are the few of those characteristics, or you can say that processing parameters. So we have the bed of 200 by 250 by 200 millimeters. So diameter of this filament which accept is 1.75 millimeter. Extruder diameter is 0.4 millimeters, where the solution will be dropping down and will be curing. So maximum temperature 270 degrees Celsius can be the material be used to deposit and print the part. So direct drive all metal dual extruders having the accuracy of dimensional accuracy is very important. So 80 to 50 micron in the range of that one due to the curing effect as well as the heat retardation effect. There is a still dimensional stability issues in all 3D printers, so we need to do the post processing to achieve the exact surface areas also. So maximum speed 200 millimeter per second minimum, and then we use this for the particularly laser precision to have zero point 0.1 to zero point 0.3 is the range of that one, and we printed the part which are shown over here using these machines. Then the next page is to test it. So tensile, flexural, electrical, resistivity test to understand what is the electrical conductivity of that 3D printed coupons or material is having. And then we did the microscopic analysis to see whether the CNTs are really dispersed properly, and what is the EDS analysis says what's the percentage of carbon has been whether increased, decreased, to understand and know more about the 3D printed CNTs with ABS material that was been done. So this is how the test specimen as per the D638 we printed flexural coupons also we printed using the ISO 178 rectangular specimen, dog bone specimen, and then we have the UTM of 100 kilonewton facility of all accessories using extensometer. We have also data acquisition system using strain gauges for the all static characterization, tensile bending, flexural, shear. All the characteristics can be, mechanical characterization can be done on this setup available in VJTI in Center for Advanced Material Research and Innovative Manufacturing. This is a fixture which 3-point bend testing can be done is the actual view, and this is how the 3-point bend test can be done with each one over there. Then we pull those samples and those tensile result shows over here. The natural ABS is blue, whereas the 0.1 has shown the highest energy to fail the material. It's shown with the red, and therefore up to 0.1 it has shown the improvement in the tensile strength, whereas adding with the 0.2 and 0.3 has drop in the tensile strength of the specimen, and that's how it plays an important role to understand adding more doesn't support for improvement in the tensile strength. Few of those failed samples under the UTM are shown over here. They broke in between the gauge length only, sometimes very close to the neck, but within the gauge length all the samples broken properly. That means consistency and curing has been occurred that we can judge from the tensile result. And if you compare this tensile strength, what 21% has been increased, then here you can say from the graph 12% roughly has been increased with 0.2 and 0.3. It start decreasing very less. Similarly, the flexural test also we did for the samples, rectangular samples, and the natural ABS has more flexural strength has been shown, whereas the adding with the CNT's flexural strength continuously reduced. And that shows that the more is CNT has been added, larger chances to that means more chances to reduce the flexural strength due to the brittleness of the specimen by adding more CNT has been shown. So this is how a drop with the first one and second and third has been compared in this table to about the flexural strength. Then we want to see what is the the thermal conductivity has been improved using the 3 probe electric conductivity test method, which we use from the VJTI electrical department, as well as we did the similar testing at VNIT facility. And what we have seen is the continuously adding of the CNTs over here. You can see the increase in the conductivity. It has been improved with the percentage, and continuously adding more can increase the thermal, electrical conductivity has been shown over here. This resistivity test is reciprocal of resistivity is the conductivity. So it has been shown with the different temperature and voltage for the particular natural 0.1, 0.2 and 0.3 on this graph, and same has been compared in the coming few slides. We also did the SEM analysis to understand what whether they are what are the air pockets or what are the bonds has not been developed properly. There may be chances to reduce the property maybe in the flexural because of such kind of air pockets also not properly cured also. So there is still curing curing has to be addressed in the 3D printing so as to avoid more and more such kind of defect and avoid those. We want to see whether the CNTs can be a similar way it will be dispersed in this one. So at smaller scale size, if you go over here from point natural was looking like this, point 0.1, point 0.2, point 0.3, and this is from the presence of CNT, similar kind of forest kind of array of the CNTs what we see under the SCME of the after getting it that means buying from the vendors. So at 200 nanometer the CNTs of arrays was showing like a forest. So that kind of structure we have seen over here with the close lower image size of that one. Then EDX analysis we perform on that one to understand more about what kind of elements are available and the energy dispersion X-ray spectroscopy, what we say. So we did the EDX. So carbon have the highest percentage, nitrogen, oxygen, nickel, and these are the phosphorus which are shown in the some of those images. But carbon has shown highest percentage, and then we also did the statistical analysis to see what kind of uh, atom percentage or weight percentage of carbon. So carbon, nitrogen, oxygen, phosphorus, nickel, these are the major element detected in the EDS analysis. Continuously we see 73, 77, 79, 79. So those are the percentage increase in the carbon has been seen, and that gives the improvement in the electrical conductivity of the ABS with CMT. So the result what we have seen from this one is 22 around 22% improvement with adding a zero point 0.1 MWCNT in the ABS has been seen as a outcome. Flexural strength the drop maximum to 15%, so not advisable to see more in the flexural applications. And electrical conductivity has shown the improvement, continuous improvement is possible, but you have to tailor those weight percentage and see which property you want, electrical or mechanical properties can be one of the way of improving the properties. But you cannot judge increasing electrical conductivity will also increase the mechanical properties because of some of those defects, and 3D printing angles has also played an important role to improve those properties. And there is a lot of scope to develop those 3D printing material. Similarly for the graphene also we followed the same methods for the graphene. So in the manufacturing of those spool, and we conducted the similar this one. So graphene is an incredibly strong material with the tensile property greater than like 130 gigapascal, which is more like around 250 times greater than the steel. It is composed with, you can see over here, a layer of single layer of the atoms formed with the inside of honeycomb lattice structures. You can see graphene also provides the highest conductivity measured up into the Siemens per meter, and presence of your graphene can enhance conductivity strength of the bulk material and help to create the composite with superior quality. And this is how the graphene sheet 100 nanometer has been seen. TM can show the actual image, such kind of image, but we could not do it. But SEM has shown this is the graphene sheet which was looking like when we bought it from the vendor. Then same way we followed the method of adding the ABS with the nano graphene powders, which was added with the same. This is from Nashik, one of the vendor we have. So we mix with this graphene again with the pellets, and then we followed this mixture to maintain the spool diameter which we have like 1.75 millimeter diameter. And finally the filament is automatically wound about the 1 second. So this is the setup, same setup. We just changed with the say, replacing the ABS with the graphene in this super, and then it passed through this particular stages of the extruder, and finally we wound it and made this one. So my student who work on that one, Bora, who work on that machine, and he prepared his own. He is pouring on the hooper. And then you can see this is the extruder which will be this is actually hooper in which he is pouring right now, and then it passed through. This is winders where you can wind it up, and this is how the spool was being prepared on this particular setup to make our customizer at Nasik facility. Then he also printed 3D printed material with the size of using this particular material, and then he did both tensile and flexural testing for the graphene to see what properties can be improved. So if you look over here, natural, you can see here is the tensile strength. If you look over to the ABS with 0.1% rate, 0.2% and 0.3% has continuously highest strength has been followed by the graphene ABS material, Nanocomposite printed by using 3D printed. And this is how you can see 24, 30, 30.3 and 29 little bit degrees, but it has shown continuous improvement on the natural ABS by adding the graphene in that one. Even in flexural also you can see those declining in the flexural properties we have observed as compared with the previous CNT ABS kind of nanocomposites. So this is how the natural has shown the highest, but as you keep adding 0.1, 0.2 and 0.3, start declining those kind of flexural strength over here. Okay, so SEM imaging we also did for the same sample with the graphene with the natural ABS, and which has shown this kind of brittle in the nature or rough kind of surface, means good kind of bonding has been done. Less pocket has been seen as compared with the MWCNT, and it has improved the mechanical property continuously as compared with your CNT ABS. So 0.3%, 24% tensile strength increase, decrease the flexural strength, and there are also effect of like depositing angle. What we see, we always deposit with 45 degree plus 45 only. If you have done plus and minus, it can be it might have been improved the the other properties better than what we have so far achieved. 24% is the outcome of this research. This research is also published in the Nanocon 2018 at Pune. So G code and 3D printing has the scope to improve. So this is what the direction of deposition was there, but you can change the direction, or you can make one layer of plus 45, one layer of minus negative 45. If you do it, there is a possibility to increase the 3D printed mechanical properties. Then we also did the EDS analysis to see whether really the graphene having the seat of one day seat having those carbon, so carbon also pop up with the highest percentage 65, 73, and then we have the others. Part one is like 78%. We can see over here, and these are the graphs which are captured from the. Then 77, 76, these are the EDS 0.2 and 0.3 we have seen. Then also we conducted the same resistivity test for this kind of separate fabricated material. So this is what the comparison has shown. The improved in the electrical drop in the increase in the resistivity. That means you can see with the certain voltage. So here there is a very low values what we see of those like rate, and this 1.2, 1 and 2 have shown between 20 to 25 voltage, very low resistivity. So it gives the highest electrical conductivity. So the conductivity test for at particular voltage what we followed, but increasing voltage also plays an important role. So at this particular low voltage 15 volt DC, so 0.3 has shown the highest, like around 300 Siemens per meter is the highest thermal electrical conductivity has been shown as compared to the natural as a zero. So it has been exponentially increased the electrical conductivity of the graphene with ABS nanocomposite, which are printed using the 3D printing methods. So this is how the some of those imperfections what we see at the different voltage, and maybe the FDM process having some of those pockets or maybe voids, maybe again the problem which may be the insulator to see those kind of variation in the conductivity, and those folds also plays an important role from this one. So what we have seen from the entire this VJS analysis, tensile electrical conductivity, this is so overall 21% with 0.38% of graphene in the ABS has been improved with decreasing the flexural strength. Then electrical conductivity has attributed to the those imperfections are there, but still it is improving the your electrical conductivity. If you reduce those bubbles and air pockets, this property will again improve a lot. That's what the graphene has given the clear indication from the outcome of this result. So to increase in the conductivity opens in the opportunity of in the application of electrical circuit boards where you are looking for the some kind of conductivity properties are important. So 3D printing those strength, stiffness can be also possible. Now we did 3D printing of the natural ABS with the graphene and CNT. Now we have also a separate research by a PhD student whose thesis is submitted. He worked on this infill patterns and percentage infill. So we choose multiple carbon nanotubes and ABS again as a material to fabricate using the FDM process. So this is also from Sampi published paper 2021. What we did is in this case is what we have. Let's go with adding those as our previous ABS with multiple carbon nanotube has given clear idea about the improving the mechanical properties. So what we choose that one to see by changing the infill patterns and percentage infill, whether the electrical and mechanical properties have any kind of influence on the ABS with NWCNT. So we again went back to our vendor to prepare our own spool, and then we added the weight percentage what is been followed in the previous research like 0.1, 0.2. Then selecting the infill patterns and percentage infill is the key objective of this research, and then print those using the dual extruder 3D printer available in our laboratory. So testing and analysis, and then what are the properties what we obtained and what are the properties previously obtained has been compared over here. So the motivation came from the first research what we have seen 15.3 and 25% those tensile strength increase and drop percentage what we have seen over here. So this is a flexural drop, this is a tensile improvement. So these two properties and decline in this property has motivated to go with the infill pattern. So what is important over here is to see variation of infill patterns such as full honeycomb, grid, rectilinear, and triangular. These four infill pattern we selected, which have shown the geometrically higher strength in the regular kind of material what we are using. So same kind of grid patterns infill patterns we have chosen for this particular analysis. And then infill material percentage is very important to reduce the weight as well as reduce the use of the material. So what we did 100%, 50 and 20. These three comparison we have taken for this investigation. So let's see. So this is what again we did the key work I can say in this research was to again produce such kind of spools initially, and then 3D printing is a major one. So we developed the different 3D model with the weight percent and fill patterns. So this is what 0.1 with the full honeycomb grid, rectilinear, triangular pattern with 100%, 50%, and 20% of the material. With ABS, we used the same way. Point 2, again we use the same pore patterns with the infill percentage. Point 2 with the pore patterns with 3 infill percentage we choose. So this setup is again common for us to produce this one. So we did the again the clear morphological characterization of what the MWC we bought it from the vendor from Jharkhand, and this is how the actual images after doing this SEM analysis. These are the forest of the multi-wall carbon nanotubes look like in your particular all those images having the 2 micron, 1 micron, 1 micron kind of. If you go in nano, you can go and see those kind of new. This is how. So what we prepared our spool, and this is how the this image the images in this slide represents and indicate natural ABS. If you melt it, it looks like a watery one, but pellets are mixed, so you have the mixing with pellets. So weight percentage accurate has been taken, mixed, and then it is passed through the mixer, you can see over here, and then heating at raw material, and before it poured in this same one and extrusion steps. And then this is particularly what we have. Solid space is the agency work for us. So 3D printed customized spools, all three variations, 0.1, 0.2, and natural ABS was white, was printed. So this is what actually we printed the natural ABS 3D as per ASTM 368 and rectangular like this using our 3D printing facility. Now the very interesting things in this research is to go with your types infill patterns for the 3D printing material samples. So this is honeycomb, but we want to print the material with again with the specimen size like a dog bone shape seen in the previous research also. So we directly created the model of dog bone shape by incorporating the honeycomb structure inside it, and that was the one layer. So layer by layer honeycomb structure, shape has been deposited, and such kind of specimens are built using 3D printing facility by providing the STL file to the 3D printer. Similarly, we also printed the rectilinear patterns to print the dog bone kind of shape. You can see the rectilinear patterns was been created over here. Then triangular patterns, you can see the triangular patterns in the one layer, second layer, third layer, like that, to maintain the minimum thickness required for the ASTM. And then it was a grid per kind. So grid also created. So all these 4 different infill patterns modeling was being done using the CAD modeling, and then CAD software, and those models were taken for the 3D printing. So here you can see the specimen with having 100% fill, and this is the with the dog bone kind of shape, and this is your lecturer testing specimens. So this is for the natural ABS with 100% without any. So this is 45-degree infill was been done, deposition of those layers was been done, and then it was taken for printing of those ones. So if you look over to the volume percentage, what is the volume? So 20% volume, you can see the same kind of infill, volume percentage. 20% with the rectilinear, you can see grid patterns. Then 50% if you do, and then what we did, the 100%. So the bottom layer and top layer we use with the 100% with the same kind of grid. So the yours models, 3D printing models were looking clearly with the changing the percentage of infill material in the grid patterns, in the patterns of printing has been shown over here. This is actually how the specimen was looking with the cross section of infill pattern with grid, and it was fooled and it was tested using the our setup available data acquisition system, and we did the full characterization for Poisson's ratio or Young's modulus so as to do the further analysis in the APM if these properties are required. So this is natural ABS with 100 fill with the rectilinear one was prepared like this. Then using the strain gauges, we have the Koya data acquisition systems through the channels we connected, and we pull the data acquisition system on Simazo UTM machine, and we captured those properties for the tensile testing of 3D printed material. So here you can see infill patterns rectilinear. So first for 100, 50 and 20, so we have seen the tensile strength 100, 30 megapascal, 25 megapascal has been shown in the natural ABS. Standard deviation is also captured so as to understand what are the curing defects or imperfections has been occurred during the 3D printing of those kind of materials has been shown over here. So 0.5, 0.7, those are the those standard deviation. So if you look over to the maximum in for the grid also, we did for the 50% and 20%, full honeycomb 50%, 26 megapascal, 20 also almost same, rectilinear 30% and for 50%, and 20% it was 28 megapascal. So what we have seen from this analysis and comparison of those tensile properties of the all 0.1, 0.2, 0.3 weight percentage in the all 4 weight percentage, including the infill percentage of the material while printing this 3D composite of the tensile coupons, which we later did the testing on this one. So rectilinear has shown the with 0.1 weight percentage of highest improvement is 36 megapascal, whereas by adding with others they have shown the drop in the mechanical tensile strength continuously, whereas the rectilinear triangular element has shown better as a second place as compared with the rectilinear in the 0.1%. 0.2 also, if you compare 0.2 weight percentage in the rectilinear also shown the highest one, and similarly triangular also shown in the similar pattern of the behavior, whereas in between other grids like what we have seen with percentage infill with the grid and honeycomb also shown a little bit drop in the mechanical properties has been shown in the 0.2 weight percentage of MWC and T. If you go with the 0.3 weight percentage, there is a continuously drop, whereas in rectangular it has shown with the 100% infill improvement of 24 megapascal. But as you keep comparing with the grid, it is continuously drop for 100%, then 50% drop. The honeycomb also almost reached the same value. That is what one of the key indicator of the honeycomb, and again it has been shown the drop. So this is what the comparison we did. What is the effect of infill pattern and percentage infill infill patterns, 4 infill patterns with their percentage on the adding the weight percentage of my MWCNT has been thoroughly understood and analyzed over here. So if you look over to the tensile strength, so with the those natural ABS components what were pulled and seen those. So here 0.1% highest has been shown. Those colors you can see with the rectilinear and rectilinear with 100 and this one. So 50%, 20%, 50%, 20%, it has shown the 36. So similar behavior has been seen in the first category rectilinear. Same if you compare and see over here has been shown the behavior of the material. What we see like 50% and 20% dropping, but here again drop in properties has been shown to the grid pattern. In the triangular pattern also, if you look over to those properties, they have shown almost like same kind of drop in the all 0.1 with the 50%, 100% and 20% percentage infill. Here also you have we can see here drop in the properties. Honeycomb also shown the behavior, but some properties are improved by adding with the 0.3 24 has been shown fill patterns. So after comparing of this, what we have seen the infill wise tensile strength of this one is to see 100%. You can see over here rectilinear has shown the 1% is highest, that is the one of this. Then here also rectilinear with point, 50% is also shown the highest property as compared to your natural ABS. Then remaining all have shown the dropping, but still there is some kind of what we say, the design of experiment has to be done and see those analysis by using Taguchi method. Can we play those effect and see the exactly any kind of improvement? And again, you print accordingly and develop those kind of patterns over here. So as a result, clear improvement and some kind of drops property has been noted over here. 0.1% of MWCNT with 100% infill has shown 22% improvement over the natural ABS. 0.2 with rectilinear has dropped, again reverse way. 0.3 with honeycomb also highest drop has been shown over here. In case of your 0.1 with the rectilinear with the tensile strength, if you want to see as the three important properties over here. So highest is this, second is natural triangular, and third is this one. So this is the clear indication of this research, playing with the infill patterns and percentage infill with adding nano material, which is multi-wall carbon nanotubes. Weight percentage has improvement in the mechanical properties is the key outcome of this research has been shown. These are the images after failing, and then from the research, what we conclude is 22% of improvement in the your percentage point weight percent of MWC, and it is found at the all ABS with a large amount of plastic deformation has been occurred, and you can see those adding up CNTs, the plastic deformation is reduced. If you see the behavior of those stress versus strain graph, as well as the brittleness has been increased by adding those more weight percentage in this different kind of infill pattern, as well as the percentage field. So those SEM images also give the clear idea about increase in the properties because of the availability and existence of the MWCNT. So those percentage infill, as finally you can see 36 per megapascal, rectangular 30 megapascal, and 20% has shown 28 megapascal. So these are the key improvement which you can choose for further development. Whereas 0.2 and 0.3 have different infill pattern, shows always decrease in the mechanical strength and can be improved later out. But currently you can go with these three outcome: rectilinear, triangular, and triangular with 20. So triangular with 50 and 20%, and rectilinear with 100% have better improvement in the mechanical strength has been seen from this particular analysis. So we can do it and improve those properties. So flexural is also there, but here I'm not sharing. It's under the review. So next one is we can go for the other examples, what the other peoples are doing for the continuous 3D printing in the aerospace applications. So this is from the SAMPI 2021, Boone Lockheed Martin Aeronautical Division. So far what we have seen is improvement in the 3D printed material properties, what we are targeted to improve the properties. Now let's see what we can do in the 3D printing development. Give me 1 second, let me have water. Okay, so this is what the material development has been done. Now, how do you develop the 3D printing facility for large future facility? So most of those mechanical properties of the composite, what we see in the through thickness, or what we see in the interlaminar shear strength, they are very weak laminated composite also. So those attempt has been made by the various researchers to improve those using the either jipping method or improving damage tolerance regime, or maybe 3D weaving. Or in my research in PhD also, we improved by using interleaving the glass nanofibers between the laminates has been improved almost like 18 to 20% of interlaminar strength. So that the people are already working on that one, and continuously people are working. But how do you develop the system? So this continuous composite cover Align ID, which is called as continuous fiber 3D printing, they have developed a trademark. And using this particular method, what they have started building the 3D continuous 3D printing mega structures from 2015 onwards. But very early they started this research in the additive manufacturing continuous 3D printing solutions, and was been recently been used in the Lockheed Martin and sponsored by US Air Force Research Laboratory, and looking to adopt such kind of techniques. So what is this one is, look over here. So these are the robots which will be having a complete your extruder attached with that robots. So you can build very mega structure using such kind of robotic arm. Will be having your particular extruder, big extruder. So it is just like a big 3D printer, not like a, customized box kind of or 3D printer. So robotic. So this is a particularly robotically manipulated end effector disperse impregnated toe of the composite tape, which are compacted on the previously placed the material over here. So you want to print. So this is one kind of channel has been printed. So this is outside of this chamber. So inside all this there. So here this is extruder. The entire tape is passed through the nozzle, like what we have passed so far. The nozzle is a wire, but now in this nozzle you can just pass through the tape, pre-preg tape of certain width, what we want to print the width of that component, and you deposit according to the G code and STL file. And once you deposit the parallelly this blue line what you see over here, it continuously cures. So you stick here, start curing, stick here and start curing, and this complete height has been built by using this kind of motions of your extruders. So this is currently people are using in the industry to build the big kind of continuous 3D printers. So what is required for this kind of 3D printing is we can have several version of the end effectors, motion strategy between them, and then you can use this is with the photochemistry is required. So what we need to work with this is a 3D printed is, you can use any cell fibers whatever right now available in the market. So you can go with the carbon fibers pre-preg, glass fiber pre-preg, ceramic fiber pre-preg, or armid fibers, Kevlar fibers, Spectra, then Xylon and Dyneema. So these are the fibers which are available, and you can use in the form of wire fiber, optical fibers can be used to print that one. So this material now people are using in the industry to print and develop such kind of structure using the available material and choose the resin, and you can cure it. Okay, so few of those software what is required to do this analysis is traditional APM or topology optimization softwares are required to have such kind of package facility and infrastructure to analyze and see the physical and geometric as well as the material characteristics to create and validate the motion of that particularly, and to get that one. So what this schematic diagram of the composites, continuous composite I have taken with the print. So here what we do is one second. Hello. Yeah. मी एका टॉक मध्ये आहे, थोडस एक 1:30 वाजता फोन करा. Sorry for the disturbance. So what we have a dry fiber spool, maybe a carbon, glass, Kevlar, metallic wire, and all those things will be wound down here. it will be passed through the dry fibers. So this is a resin bath. So through the resin bath, this is passing. Resin bath is maintained as it stick and take out the resin. So this level will be maintained by using the resin bath. So impregnation will be done over here with the variable fiber and volume fractions, and it will be coming through this one, and then it pass through the roller. So this fiber may be having a width, let's say half meter, 500 millimeter of width. A complete ply is passing through this bath, and it is going like this one. So this is what the passing through the roller will squeeze and excess resin will be taken out, and this energy source what we are using, like maybe UV or heat source or maybe laser, will be exposed to make the snap curing, the compact curing with the bottom layer, and very big structure you can develop it. Okay, so this is how it exactly in our this setup is shown over here. So this particular ply, dry fiber ply, will be passing through the resin bath. It will impregnated with the resin. The excess resin will be taken out due to the passing through the roller, and it will be depositing on the next roller. So this work as an extruder. What the extruder was depositing, this work as an extruder, which will be just depositing, and the roller will be moving like this one. So this system will be outside, but we are maybe on this robotic arm, and it will be developing such kind of 3D printing facility, 3D printed component, big mega component, maybe having width, let's say I mentioned here 500 millimeter of width. So it will develop a thickness of, let's say, for 10 millimeter of thickness you want to develop. So that will be number of layers will be analyzed initially, and we will pass through that, and parallelly those curing action can be done very easily. So it has a wide example in the aerospace application and having the challenges also, but people are right now using this kind of facility and creating the state of art to develop such kind of manufacturing. So despite of those curing challenges and all those, people are still working on those features like automations. If you do it and feed those plies of the fibers through the resin bath, and you can deposit, and you can make a low cost raw material and high rate of material deposition that can be avoided. So currently US Air Force has established a vision for the low cost attritable aircraft program, which will be developed for a single purpose of unmanned platform, which will be used in the mission for the moon, moon as well as Mars, to send small aircraft, or you can develop the small aircraft over there, and they may they may fly and do the surveillance or other operation on the planets. So that is what they are right now looking. So they want to build over there, not on the earth. So take the material, go over there, build this kind of continuous fiber 3D printing method, use the continuous fiber 3D printing method, and develop those parts. So plan to build such kind of this aircraft. So built with the having short time frame, no such a low cost, as well as enable them to a mass and incoming future work. So what they want to look their aircraft when they will go on the moon or maybe on Mars, it will be kind of like this one. Okay, so this entire structure, you using the robotic, you can do it, only the frame you can send, and you can have your system built inside it. So the structure can be built and printed with the help of using 3D printing method, what in the continuous fiber 3D printing method right now in the development stage, and people are using in the industrial applications. So this is one of the example they looking for the futuristic application and see those ones. Then this is how we can go for the digital factory, what people are looking for the industry 4.0 or maybe Internet of Things, and want to make their digital factory for the future. So autonomous is the main goal of the making the industry 4.0. Will be having your robots and those kind of material supply system, control system using the Internet of Things, and then you can make the manufacturing with lesser the assembly over there, and you can have such kind of manufacturing process in coming days for the mega structures and high accuracy, and make a less component in the manufacturing. So with this digital thread running from the design through the manufacturing to the service life, and is not continuously made by the robotic program, but it will be coming very soon, and people will be having the entire structure built by the this kind of manufacturing setup using the automation very soon. So this is what the virtual environment, how this kind of the aircraft, what you see, which will be flying on the Mars or moon, will be fabricated by the robots in the same fashion. So this is a structure, structural element on which this particular structure will be built by using such kind of robotic arms. So four robotics will be building structure from beginning to end. Entire one structure will be there. So less manufacturing assembly will be there in the coming days. For example, having such kind of unmanned air vehicle, which will be built. This is Lockheed Martin, facility they are developing. Want to develop this facility autonomously, can be controlled from the Earth base to the, whether it will go for moon or this one Mars mission. Will be building such kind of aircraft very soon in coming next couple of decades on this one. So future is topology optimization is very important one. So you can reduce the mass and increase the mechanical properties by having such kind of topology optimization. So functionality, multifunctionality, functional smart material also put on their structure so that it can work as a sensors and give the signal to the ground base, and no need to install another sensor. So embedding the sensors and putting the sensors in the 3D also playing an important role to produce such kind of 3D printing in the coming days. So those fibers, wires you can put, and you can embed those fiber optical filaments, nichrome wires, and manufacture can be done. So these are the metal. Fiber optics has been kept over here. LED has been built during the manufacturing itself. These are the copper wires. They are also passed through while 3D printing. Then nickel, nichrome wires also pass through this particular kind of printing of this kind of wing. So this is, you can say, the aerofoil having such kind of 3D printing with the internally metal structure support has been done. So in conclusion, 3D printing is a new class of advanced manufacturing, you can say the additive manufacturing, which enable the low cost manufacture for high performance composite structures through the end effector continuous, and you will have the your fibers, impregnated resin with UV snaps curing systems on it. Also the toolless features, combination of the full automated additive manufacturing will be coming soon, like what the new families of Air Force, unmanned air vehicle, UAV design, or low cost treatable aircraft which we want to manufacture and use, like India also doing the Udan. They can also think about such kind of manufacturing of the low size or low capacity aircraft. Future development will be continuously, resin, what kind of resin, then product and effectors, how we can develop those and optimize those parameter and processing, demonstrating, and those multi-functional capability in the structural integrity. This is one area. Then another one is what I want to discuss is large scale additive manufacturing of high strength fiber reinforced polymer composite. So big, this is from the, again, one of the paper from the Sampi. So experimental setup with this is large, like bulky components, bulk structure you want to develop is the way of depositing the large what we say the big area additive manufacturing, large area or additive manufacturing, which we want to achieve the strength, and that can be done using the 3D printing with the having your multi-axle machines allowing the printing three-dimensionally, and give the extruder with the extruders having set up mobility in the both X, Y, and G and axis, and then you can have your motors with the extruder chambers, heating zones, and can be done. So this is the experimental setup what the people right now are trying to develop. The standard nozzle is this much, so the nozzle can be modified. So the axis, 5-axis controller machines, you can have carbon fibers will be continuously provided through the bundles, and then the bed will be like this, and then you can have your extruder controller using the G code programming method, NCCNC programming method, and extruder head can be here. So what the schematically this particular additive manufacturing will be there, instead of having your prepregs or maybe having your mixed material at the nozzle or the extruder level, you design your particular pallet supplies. Nozzle will be the extruder will be here only. You can pass through your continuous fiber, so this polymer will be impregnated with your continuous fiber, and then you can keep depositing, and then you can pass the UV light and you can develop. So this pallets input supply pallets as well as your continuous fiber through this particular toe will be coming, and heating of this polymer melted, and you can control those kind of 3D printing for the large structures. So some of those structures which are built over here, if you look over here, so this entire extruder will be moving on the large bed using the again automated robotic arms, automated automation, and this is what the structure they have built. The length is 300 millimeter, height is 150 millimeter, and the shape is you can see from the top view, you can see this kind of shape they have developed. So the large format additive manufacturing, this shape size is possible, and you can develop the system by enabling those production of low cost, high strength, large formation of samples in such a small times, because faster is the curing those kind of selection of the matrix and the fibers in the additive manufacturing. Filament can be depositing quickly and your component will be ready, so the time will be saved with the help of. So this is particularly made up with the PLA material, with the continuous PLA is a matrix, and your carbon reinforced element. So the carbon fiber was impregnated and then it was deposited. So you can have the chopped oil fiber, people have already developed, but continuously. This is the setup, what you see, thin wall structures prepared using the short carbon fiber reinforced ABS pallet. We also did the ABS pallet, but these guys use the short fiber of the carbon. They mix in a big such kind of extruders, and they nano cone mold. They have developed this kind of particular 3D printed, your structure. So in this kind of, you have big such kind of curing ovens for the thermoset resin, maybe autoclave methods. But if you have such kind of extruder, what you see over here, and these are the controlling elements, you can build such kind of element over here, or you can create a chamber, and inside the chamber entire extruder will be moving as a robotic arm, and you can prepare such kind of large 3D printed the shape and size of high strength, low cost material with rapid cooling methods, and throughput is in a short duration of time. So again, the conclusion from this large area additive manufacturing is proposed manufacturing techniques enable the rapid and inexpensive fabrication of high performance complex structures using the continuous fiber reinforcement. So fiber is coming and matrix is coming different way. You are melting, making impregnation and building. So with an ability to rapidly print the complex, large net shape structures. So this is what you can see over here. This method also, process a low, cost-effective solution to rapid fabrication of the strong and, inexpensive continuous fiber reinforced, functional composites. So you can put the functional, your wires, your sensors on these structures while printing the same one in quicker way. So this is what we are doing in the 3D printed area. We also developing some of the nanofibers. Those nanofibers now we want to use in our 3D printed materials. So what we have in the nanofibers using the arc spinning method. So PAN is a precursor used to produce your carbon nanofibers. So using the arc spinning methods, what we have done in this electrical and mechanical characterization and morphological characterization. So electrospinning is one of the process to create the continuous fiber from the precursors, so widely used for smooth and ultra thin fibers. So this pan fibers is this is the electrospinning setup. You have the collectors and you have the syringe pump. The distance between these two, a voltage difference is applied due to the voltage difference and solution viscosity. The Taylor comb will be formed and the fibers will be pulled and collected on the collectors, and that's how electrospinning generate the fibers. So in this case, what we have developed is our precursors with the pan with the DMF solutions, and then we mixed it and at the 60 degrees Celsius for 3 hours and then cool to the room temperature. This is how we have the setup, and we do the regular preparation of the pan solution which go through the spinning to produce such kind of fibers. So pan powder is polyacrylonitrile powder with the molecular weight of 115,000, and you do the heating and you can control the rotation of that magnetic stirrer, and this will be steered properly. Once that solution is done, then we can fill that solution in the syringe pump. So needle is there, one voltage will be applied here, another is here. This is the electrospinning setup. This spin electrospinning automated setup available in our laboratory. We produce the fiber using this one. So voltage controller, syringe pump controller is here, and temperature controller unit is this blower is here, so that the humidity will be also controlled in this chamber. So using these flat plate collectors, we can directly collect those fiber due to the voltage difference and viscosity of the solution, voltage difference and Taylor comb will be formed, and because of that high surface tension, fibers are pulled out and collected on the collectors. So these are the non-woven fibers. So we have optimized some of those fiber, electrospinning with the help of flat plate and drum plate collectors. These are the optimize the parameter which we have set so far and published this research in the Vasset Journal of Material Science and Metallurgical Engineering, International Journal. So 15 is the distance between these two. Applied voltage 12, processing duration 2 hours, syringe capacity 2, flow rate is 1 millimeter per hour. Relative humidity is controlled and kept as 54, and we have obtained such kind of flat sheet collector, isogram collectors, and then we did the SEM images to see what are those fibers size morphologically look like under this analysis, and those are fibers in the range of flat plate collector 450 60, rotating drums 350, flat plate with the carbonization reduce the diameter 360, 5 nanometers, rotating 280 nanometers are the achievements. So this is heating, stabilization, and carbonizations are the process after the electrospinning. So this is before the after the stabilization. This is after carbonization. The fiber get shrink and chains are get arranged, and you get the purely carbon fiber, 99% of the carbon fibers. We did the FCM images, and we saw the clear cut fibers at the 200x and 1200x with the particular diameter what we seen like 465 and 285 of the fiber diameter. These are the fibers what we see under the same images for the flat plate collector. These are the fibers which are collected and the same images obtained at higher resolutions you can see for the flat plate collectors. After carbonization, so this is before carbonization. After carbonization, the fiber get the chains get attracted and fiber gets shrink out, and this is how the fiber look like after carbonization at 700 to 800 degrees Celsius. And then we did the electrical resistivity test to see whether the fibers possessing a higher conductivity or what. So this is three probe fiber electricity test method available over here. We using this formula R is equal to 1 upon rho into rho is the resistivity what we obtain. So length and cross section of the fiber is given, and then accordingly what we found thickness of the fiber we having a 1 mm thick, probe distance 2 mm, and then what we have seen at different temperatures 30 voltage this and the conductivity. So as you keep increasing the voltage, the conductivity has been significantly improved by reducing the voltage. That is what we have seen from the resistivity test of those fibers. Viscosity also, the best viscosity what we have seen is the 76.6 is the best viscosity, which gives the average diameter will be 350, lower will be 250, and highest will be 3. This is what the statistical fiber and SIM fiber analysis has been given. As you keep decreasing the fiber distance, collector distance, fiber size will be increasing. So optimal will be your distance. What is shown over here is 20 will be the lowest one, but we have maintained optimal distance. Thermal conductivity with increasing temperature has been improved, has been shown over here, and those fibers will be before and after carbonizations are 365 nanometer and 280 nanometer. For optimum voltage is 12 and 13 kilovolt, and those fibers now they can be used for the functionalization of making functionalizing material, and then these fibers can be used for the 3D printing. So what we have done is the synthesis with those fiber, again adding with the materials, nanoparticles. Titanium dioxide as a nanoparticle has been added, and we have prepared some of those fibers. So this is what we have, the same recipe, but titanium DMF, pan DMF with titanium dioxide was added, and then helps spun to see what the fiber we get it. Then after the spinning, stabilization, carbonization, and then see what are those morphological and electrical properties look like under this particular analysis. So what we have seen, those mixing with the nanoparticles of titanium dioxide in the DMF solution setup has been shown over here, and then we use that 0.58 percentage for titanium dioxide particles in the solutions. This is a recipe, and then we mix it and sonicated using the sonicator to disperse the titanium dioxide particle in the DMF pan DMF solution, so as to obtain the uniform distribution or dispersion of the nanoparticles in the fibers. So this is how the solution looking after this having the sonications. 8.1 gram of pan powder with added 1 in the solution 1, and then we did and then we use this image for this is a particular setup where we started LF spinning on the flat plate collector as well as a drum plate collector for the pan titanium dioxide nanofibers. So on drum collector, this is how drum was collecting the fibers which will be coming from this particular spinneret tip of around 2 hours. So these are the processing parameters which are set for the pan with the titanium dioxide to obtain the good quality of the fibers, and those fibers which will be taken for the stabilization for 280 degrees Celsius, and then after the stabilization it took to the carbonization in the CVD chamber at 700 degrees Celsius. We have the setup of CVD chamber, and then the fiber becomes like very shrink one, and then we did the carbonization the analysis as well as those fiber analysis to see how the fiber looks after the carbonization. So those morphological properties, 600 nanometers, the fiber size has been increased. Edx analysis we performed to see titanium dioxide is present or not. So we saw the titanium dioxide presence, and this is Edx analysis graph shows the clear indication of those available titanium, and those are the noise, but we put just for the reference purpose. So this is what we have done, and those fiber now we will be using carbon fiber to produce the 3D printed material using the PLA as well as ABS. So we have other things, but I think due to the time limit, I will stop over here, and I will take the queries from the participants. This is the facility. What in fact I have the MD also, but I'm not going to talk here. So we have the full setup for the LF spinning, and then manufacturing of composite also. These are my PhD students. 3 of those was Sachin and Divyanka submitted the thesis. Shahpuri is likely to submit and Nitin and Amit are still working on their thesis. So 3 PhD are already submitted. So we acknowledge to the institute, JSNN as well as VJTI for providing our funds to perform this kind of research in the Cambridge Center for Advanced Material and Innovative Manufacturing and Production Department through the TCube 1 and 2 MHRD's funding. So with this, I thank you to one and all, and if you have any questions, I will take those questions.
That's really wonderful session, sir. Very much informative. There are two questions or the discussions which you can refer to in the chat box. The discussion points are given by participant Parmeshwar Ritapure. First point is it possible to manufacture metal matrix composites using 3D printing? Melting temperature for matrix 700 degrees centigrade and for reinforcement 2300 degrees centigrade. So this is the first point. And then he also has the second point to discuss is, do you have compared performance of ABS composite manufactured with conventional method and 3D printing?
All right, so thank you for this, very good questions. You are really interested and people are working in the 3D, I can say. So first is, you need to have the different setup. 3D printing of metal matrix is a totally different setup because metals are at higher melting points. So we need to, what is the method right now? The people, they deposit the particle by particle using the sputtering methods. Okay, that way you can develop the 3D printing metal for the metal. As the temperature is maximum, so you have to do the sputtering is the best way to take out the particles and deposit the particles. But like a molten form, you cannot do like what we are doing in the 3D printing. So there is a different setup. So there is a extruder is a different way of depositing that one. So we have the different sources. We have to heat the sources, take out the particle out, like molecular beam epoxy. What we take out the gallium arsenide kind of semiconductor or silicon or maybe germanium. So they take out those particles and they route it through the chamber and they deposit in that particular one. So 3D printing is possible like what we are doing right now in the polymeric, but polymer have low temperature and therefore those sustaining the temperatures and heat effect on the other electrical and other components is less in terms of your polymeric composite, but you can do it in the metal and many people are working. In fact, I want to refer the example of Boeing JE plant Bangalore. If you refer for the manufacturing of the engine turbines, okay, so those engine parts they manufactured using the metal matrix printing. Metal matrix printing, out of 1,000 parts they converted into the 350 parts. So they created such kind of small assemblies in a complex shapes by using the metal, and they assemble it and it became like 350 parts instead of having the 1,000 parts. So all the like electronics parts also you can pass through those channels if you are provided regularly. You can pass through your particularly those shapes. You can use the shapes and size to the small parts, and you can convert the engine shape into the small number of sub-assembly components. So that is right now the people are working, people are developing the critical and again the cost plays a very important role if you look over to the metal 3D printing, because our conventional manufacturing have very low cost. So people are still in the dilemma to whether to use or not to use. That's going on. Regarding that is I think regarding your first question. Second question is your ABS. Right now people are using the extrusion method or die casting method or sheet molding methods they are using, and they are preparing it. So whatever the natural properties I have shown, the same properties they are getting, but to mix that small weight percentage in the conventional way and manufacture it still it is in the development phase, because there are large chances to occur some kind of agglomeration. So dispersion is a major issue in terms of your conventional manufacturing, where people are still not started adding proper way. Otherwise, most of the time our nanoparticle have higher surface energy, and they are smaller in size, so they get agglomerated very easily if you don't pour it or put in the dye, or maybe in a particular mold. So that is the only reason people had not added it, but you can improve it. So 3D printing is the best way to see weight percentage and fill patterns, to save the material not only in the ABS, but if you have costly materials, so you can use this kind of infill patterns and percentage infill to achieve your own mechanical properties and electrical property. So that's what I want to give the explanation on your ABS kind of related query. I think Parmesh again he put one more. Where is the facility? Where this facility is available for the research? So which facility you are asking? Either the polymeric composite or metal matrix composite. So metal matrix composite Pune also, there are few companies, they are now build their own setup. They are taking the customized job and they are building your component, but it is again very costly. They are taking a lot of consultancy and manufacturing cost. You need to bring your component and specify the material, and they have set up their own 3D printing facility in Pune as well as Bangalore, and they are now customizing customized manufacturing setup is available. They are manufacturing your part. So I think I have answered all the queries. If you have anybody, they may ask, and I will be happy to answer your queries.
Yes, participant, you can unmute yourself and ask the question. Participants may put their question in chat box. Otherwise, I think there is no more questions, sir. So thank you
Okay.
very much, sir, for such an informative session on the 3D printing, in particularly in the area of nano composites. So I will share your contact details, particularly email ID with the participant. Those who want to work in your area can definitely contact you. So thank you very much, sir, from the whole Atal team and the SPC organizing team. Thank you very much, sir.
Thank you all, and look forward for your future engagement and interaction. Thank you all participants.
Yeah,
Thank
thank you,
you.
sir.
Yeah.
Thank you. So for participants, our next session will start at 2:15, and next session is by Dr. A.M. Kuthe. Dr. A.M. Kuthe is from BNIT Nagpur. So please attend the session. It is very important session. He has vast experience in the development of 3D printing for the various medical applications. So he is very senior and a lot of experience he has gathered in the particularly in the area of 3D printing. So don't miss that session. Join by the 2:10, so as to avoid the last minute rush. Thank you very much. Have a nice lunch. Thank you.